The periodic table, history and information. Let's talk about the history of the periodic table. At the beginning of the 1800s, there were less than 50 elements discovered, and chemists were looking for ways to organize them. It was until 1829 that Johann Dobeheiner, German chemist, grouped the elements based on similarities, such as average atomic weight and densities, arriving to what was called the law of triads, three elements with similar properties. Years later, Dmitry Mendeleev, 1834–1907, a Russian chemist, working on a different way to organize the elements, came up with the first periodic table, where the elements were arranged by atomic weight, today known as atomic mass. Mendeleev's periodic table was a great breakthrough, and the fact that he predicted the properties of aluminum, boron, and silicon and other elements' properties was amazing. Henry Moseley, 1887–1915. A British chemist, he studied under Rutherford's supervision and brilliantly developed the application of X-ray spectra to study atomic structure. Moseley's discoveries resulted in a more accurate positioning of elements in the periodic table by closer determination of atomic numbers. Tragically for the development of science, Moseley was killed in action at Gallipoli in 1915. With the discoveries of isotopes of the elements, it became apparent that the atomic weight was not the significant player in the periodic law, as Mendeleev, Mayers, and others had proposed, but rather the properties of the elements vary periodically with atomic number. And this was called the modern periodic table, the one that we use today. What information can we get from each box in the periodic table? At the very top is the atomic number, which is equal to the number of protons in the nucleus, as well as the number of electrons in the electron cloud. The symbol, a one or two letter abbreviation derived from the element's English or Latin name, the name of the element, and at the very bottom the atomic mass, which is the weighted average of the masses of all elements' isotopes. Rounding the atomic mass to the nearest whole number yields to the mass number of the most common isotope. Remember, mass number is the addition of the number of protons and neutrons in a specific isotope. Now let's learn about periods. Periods are the horizontal lines in the periodic table. All the elements in a period have the same number of atomic orbitals. Every element in the top row, the first period, has one orbital for its electrons. All the elements in the second row, the second period, have two orbitals for their electrons, and so on. In total, you will get 7 periods. Now, do you remember electron configuration and the chart for placing electrons? Well, each energy level matches with the corresponding period in the periodic table. Now let's learn about groups or families. When a column goes from top to bottom, it's called a group. The elements in a group have the same number of electrons in their outer orbital. Those outer electrons are also called valence electrons. They are the ones involved in chemical bonds with other elements. That's why they are so important. The example that you can see now is the halogen group. In here, fluorine, chlorine, bromine, and iodine. All of them with different number of electrons, but if you can see at the very end, in the outermost energy level, is only one electron. And those are the valence electrons. Now, let's see what kind of elements we can find in the periodic table. The periodic table is roughly divided in 3 types of groups of elements, and these are metals in red, metalloids in yellow, and nonmetals in blue. Metals. Most elements are metals. They are usually shiny, very dense, and only melt at high temperatures. Their shape can be easily changed into thin wires or sheets without breaking. Metals will corrode gradually, wearing away, like rusting iron. Heat and electricity can travel easily through them. Examples are calcium, barium, and gold. At the very right of the periodic table, you'll find the nonmetals. And they're very different from metals. Their surface is dull and they don't conduct heat or electricity. As compared to metals, they have low densities and will melt at low temperatures. The shape of nonmetals cannot be changed easily because they are brittle and will break. Examples are fluorine, oxygen, and helium. Metalloids, divided in metals and nonmetals, are elements that have properties of both metals and nonmetals. They can be shiny or dull, and their shape is easily changed. Electricity and heat can travel through metalloids, but not as easily as they can travel through metals. Examples are silicon, arsenic, and germanium. Now, talking about metals, metals can still be subdivided in 5 groups or families. The first will be the alkali metals. The second column is called alkaline earth metals. The family in the center are the transition metals. At the very right and before the metalloids are the other metals or poor metals. The first family at the very bottom is the lanthanides, and the last one the actinides. Also, nonmetals can still be subdivided in 6 families. Remember, nonmetals are at the very right of the periodic table. At the very right, we will start with the noble gases. These noble gases usually they don't bond easily. The second family are called the halogens, starting with fluorine. The other 4 families of nonmetals are called with the name of the metal of the nonmetal that appears at the very top. For example, oxygen family, nitrogen family, carbon family, and the last one, the boron family. Now, do you remember electron configuration? SPDF? Well, the periodic table is also arranged by the different orbitals and suborbitals. The first 2 families are the S group. The P block will be in the right hand side with the nonmetals. The D block will be with the transition metals, and the F block will be with the lanthanides and actinides. Thank you for watching.